We're in 1.3. Yeah, and we're almost through with 1. Yeah.
Okay.
Did I give you all the tests last time? Okay. I may not have them run off. I'll run them off at the end of the class and get them to you. If I think we'll finish today. But I did want to say this, and you've heard it. Victor, you came in after I talked about it before. I talked about it last Wednesday too. Are you at all interested in being on the math team? Not at all? Are you a pre-engineering major? Okay. Even if you don't participate with the team, the practices that we have will be really helpful in, what did you call that? That test that you take?
FE.
FE.
Yeah.
And what did that stand for?
That stands for
Fundamentals exam that you take before you can take your PE, professional engineering degree, exam, which usually you take that after you've worked for a while. But it's not a bad idea to take the FE shortly after you finish school, while you got all that stuff fresh on your mind.
Yeah.
It's one part of that. At least one part of it is just totally math, isn't it? It used to be.
Well, yeah. It's like divided up in sections, so yeah.
Yeah. Aren't there like several different pieces
Yeah.
to it? And I think one of the pieces is math,
It is.
calculus, pretty much. So it would be a great practice, because what you do in the math team, you're working calculus problems, but you're not worried about certain forms and stuff. You're trying to figure out the quickest way to get a right answer, and you can use any kinds of setups to do it. Whereas a lot of time in the courses, you follow the way the book does it, In this, you're just trying to get it done, and the practice of doing that is a great thing to help you do it quickly and pretty precisely when you're doing things like that the FE exam. Okay, so you might consider thinking about it anyway. I know that Mr. DeRacy, who's the coach of it, you know her, Natalie DeRacy, on the Birmingham campus? Yeah. She's was really wanting some of you upper-level calculus students to participate, but even if you don't, you still may find it's useful for you to, for your later exams and stuff. All right, where we were last time, in Chapter 1, which is Introduction to Differential Equations, 1.3 is Differential Equations as Mathematical Models. And here's Emmanuel. Okay. Did you decide anything about the math team? Okay. Have you communicated that to Ms. Gracie? Oh, you haven't? Okay. I may not see her this Friday because I'm going to be over here making up a trig class, but I'll try to get it to her. But if you're in touch with her sometime, let me know. You can. Now, are you pre-engineer or math or something? Pre-engineer. I was just telling the others, it dawned on me later, and I may have told y'all last Wednesday when I was thinking about it, that one of the things that pre-engineers do is take your FE, which is called the fundamental exams, used to be called the EIT, Engineering and Training exam, and then later you'll take the rest of them as for your PE exam. But you got to get the FEs passed before you can take the PE. The FEs are based on what you did in school, so it's usually a good idea to get that done while all the school's fresh in your mind, and then later when you've worked certain times you do your PE exam. I think that's how it goes anyway.
Yeah.
Okay. Because I think some of those you have to actually have been on the job for a certain length of time. So.
Yeah.
Okay.
I think probably 2-3 years. Yeah.
Yeah. Okay, but the FE you can take even while you're in school, I think.
Yeah, you take your junior year in school, I believe.
Okay. And the thing is, the stuff we do on the math team would be very similar to how you try to pace yourself and work through problems, just random problems, however, it would be great practice for that. So even if you can't go to the thing, if you want to attend any of those practice sessions, they may be beneficial to you. I'll just held it out there. And then if you find, hey, this is fun, I'll make time and do it. That would be even better. Okay, so anyway, let's go on from here. All right, we're in Chapter 1, Introduction to Differential Equations. We should be finishing that fairly soon today. 1.3 is Differential Equations as Mathematical Models. I just wanted to give you a flavor for how you use differential equations. And we got down to page 24. We had done Newton's law of cooling and warming, the spread of a disease, and now we're doing chemical reactions. Okay? And they sort of have several things going on here. I don't really like the way they start. They say the disintegration of a radioactive substance governed by the differential equation that we did earlier is said to be a first-order reaction. In chemistry, a few reactions follow the same empirical law. If a molecule of a substance A decomposes into smaller molecules, it's a natural assumption that the rate at which the decomposition takes place is proportional to the amount of the first substance that it has not undergone the conversion. That is x of t is the amount of substance A at any time t, then dx of dx dt equal kt would be the rate at which x deteriorates, or undergoes a change, is proportional to how much of x you have. K is a negative constant since x is decreasing. So here's an example that you would do. Let me get my pen. All right. CH3, by the way, that's a methyl group, is what that's called. CCl. Okay? Now, a methyl group, CH3, is a C with 3 hydrogens. Okay? I left off, I said, I'm missing something here. There's 3 of these things. Okay? Let me just draw it this way. Here's a carbon. Carbon has 4 bonds, generally. Okay? It can distribute them lots of different ways. On one part, it has a methyl. Okay? On another part, it has a methyl group. On another part, it has a methyl. But the 4th bond is a chlorine. That's what that looks like. Now, where those are placed, it doesn't matter. That's just a representative drawing, okay, on 2-dimensional plane. Now, if that interacts with sodium hydroxide, okay, now, what you wind up with is the hydroxyl exchanging, and this is just NaOH, okay, OH is a radical. You exchange the OH for the Cl, so that gives you a CH3, 3 of them. They stay intact. The central carbon stays intact, but now there's an OH on that plus NaCl. Anyone know what NaCl is? Table salt, sodium chloride. Okay? You put on your, what you have in your bag there? Oh, those are candies there. Okay, you got some salt? Oh, you have to, okay. Okay, there's the reaction. Okay? Now, pretty simple reaction. Only the concentration of the T-butyl chloride, that's what this is called, T-butyl chloride, controls the rate of the reaction. But in the reaction, goodness gracious. They throw something in here that, I mean, I kind of see where it's coming from, but it sort of makes no sense. They throw in a methyl chloride, and why I do not know. Okay? Either they have written the formula wrong, which I don't know why they would have. Oh, no, I'm sorry. Okay. Sorry about that. This is two different things. Okay. As an example, this is a first order chemical reaction, conversion of T-butyl chloride, that's this one, into T-butyl alcohol for that one. Okay? That's what's going on. There, only the concentration of T-butyl chloride controls the rate of reaction. Because usually you have excess of this in solution. So how much of that determines how much you get of that. Okay. But, and this is the thing, they should have written this as a new paragraph. They didn't. Let me erase this because I need more room. I thought this was all one reaction, but it's not. Okay. But it's another reaction that looks fairly similar, but it's not the same. Okay. Is if you had methyl chloride, which is CH3Cl. No carbon in that, just the CH3, one CH3, a positive charge is connected to the negative charge Cl. You add that to sodium hydroxide, and you now produce, well, let me write them in the better order. Doesn't matter which order, but just to get it more looking like CH3OH, methyl hydroxide plus NaCl. Okay? In that reaction, one molecule of sodium hydroxide is consumed for every molecule of methyl chloride, just forming one molecule of methyl alcohol, that's what that is, and one molecule of sodium chloride. In this case, the rate at which the reaction proceeds is proportional to the product of the remaining concentration of CH3Cl and NaOH. Now, there's no reason given that the NaOH doesn't contribute there. It's just that you assume you got plenty of that in solution. Here, it's a one-to-one. Well, it sure looks like it could be a one-to-one up there too, but they say it isn't. So in this case, it depends on the product. They're the first order reaction if what you want it to be X. If X was the concentration of this, you would have dx dt is equal to, I like to write it as minus kx. That would be this one. On this one, however, let's call this x and this y, because you have some concentration of both of them. Then you would have dx dt is equal to minus kxy, because it depends on both of them, not just one of them. Okay? Well, no, that's not quite right either. Well, yeah, it is. But you see, for every one of these that you get consumed, how many get consumed? It's a one-to-one here, so it would be alpha minus x, where alpha was the amount you had originally. So, well, let me take that back. If alpha of this gets used up, then let's see. Okay. Say you had alpha of this originally. This much of it is let's see, is left. Okay, you've consumed that many. okay, and you had beta of this one, and you've used up Y of that, then, but these two numbers, the amount of this that you use is equal to that, so this can be X as well. So this will be minus K times alpha minus X. This is how much is remaining. Okay. It's just alpha minus X times beta minus X. Because however much is combined with this is the same for both of them. So that would be then the differential equation. Where this would be a fairly simple one, like we saw with exponential decay, with radioactive decay, or that type of thing. But here it's a little more complicated because as some of these combine, then you lose this and lose that in solution. And whatever you had to begin with, that then would determine the rate, which the product would determine the rate. So it gets to be a lot more complicated of the differential equation. That's a second order reaction in chemistry. Okay? Now, another sort of classic example that you tend to see a lot, if any of you were in chemical engineering, these things would make a lot more sense. But one that I don't know if you remember back from maybe even high school or somewhere, mixtures. Okay? Do all of you have books? Yeah, do you? Oh, you don't. Okay, let me draw the picture. Here we have a vat. Okay? And this vat has a base in it, and it has an input coming in. Something is coming in. You also have a tube at the bottom that something else is coming out. Okay? And in here you have your liquid. Okay? Now, what if you're mixing two salt solutions of different concentrations, and that gives rise to a first order differential equation for the amount of salt contained in the mixture at any time t. Let's suppose that the large mixing tank initially holds 300 gallons of salt. Okay, we'll call it brine. 300 gallons of brine. Okay, some salt solution. Okay? And that's your, what are they going to call it? A. We'll call this A at 0. Your initial amount that's in that container. Okay? Okay. It's 300 gallons of brine. Another brine solution is pumped in. Now this input rate of brine is 3 gallons. So this is dx dt is equal to 3. I'm sorry, I can't read. 3 gallons per minute. That's a rate, gallons per minute. So the T is measured in minutes. Okay? The concentration of the salt in this inflow is 2 pounds per gallon. So the concentration of the inflow is 2 pounds per gallon. Okay, that's how much salt is coming in, 2 pounds per gallon, and you got 3 gallons per minute coming in. I probably have the X wrong, but we'll go back and change that in a minute. I meant to put A anyway, but I put X. But we'll come back and deal with that in a minute. Okay. All right. When the solution of the tank is well stirred, it is pumped out at the same rate as the entering solution. So the rate out, and I'm going to call this D, and I'm going to go back and call this A. dA dt coming out is also 3 gallons per minute. Okay? Because it says it's the same amount coming out. So that means the amount in your tank at any time t is this, 300 gallons of brine. Same amount coming in as going out. What differs is how much salt is in there. Because you got 2 pounds per gallon coming in, you have whatever your initial brine concentration was in there initially, and then what's coming out is either, if this had more than 2 pounds, what's coming out is a little saltier than what's going in. If that brine concentration is less than 2 pounds per gallon, what you got coming out is diluted from there. Okay? Okay. A is the amount of salt measured. Okay, so A is the amount of salt. Okay, so I got that wrong. Let's call do they have a let's go back and call that X, like I was to begin with. That's how much is in the tank. Okay, dx x of t is equal to that. Okay, yuck. Okay. Okay. 3 gallons per minute is coming out. Okay. Now, if A of t denotes the amount of salt in here, so A of t is the amount of salt. Okay. Just salt. Okay. Now, the rate coming in is 2 pounds per gallon, 3 gallons per minute. So it's coming in, dA dt coming in then would be 6 pounds per minute. Okay, amount of salt per time, 6 pounds per minute. Okay, now we don't know how much was in there originally. So A of t down here right now is unknown, but we'll work on that. Okay? Now the A of t leaving, we don't know that one either. So the dA of t, which is the rate at which A of t changes in the tank. Okay? So this is the in the tank. dA dt, we don't know. Okay? But let's see if we can figure it out. Okay? So this is what they're calling rate in, rate of salt coming in. Okay? Now, you know you have this in the tank. This is salt in the tank. Not gallons or anything. It's salt in the tank. So the dA dt is the amount of salt, the rate at which that is changing. Okay? We're not going to go there yet, but the A of t is what's in the tank. Well, we do know it because this is A of t divided by, I'm sorry, okay. Yeah. So what we're going to call, and this is what I was calling C of t. C of t, concentration in the tank, is A of t, which we don't know how much that is, the amount of salt in the tank, and you always have 300 gallons of water in the tank. So the concentration is A of t divided by 300, because this is gallons in the tank. and your concentration is pounds of salt per gallon of water. So that's what's in the tank at any one time, okay? At any time t. The rate out is also 3 gallons per minute, but the concentration coming out is that same, so that's A of t per 300, okay? That would be pounds per gallon, okay? The C of t is also what's coming out of the tank. So this will be A of t over 100, okay, because of 3 gallons in this, and this will be pounds per minute, okay? That's the rate at which that's leaving, okay? So what we've got, that's the rate out. So the change of this is what we're looking for here. The change of amount, the net rate, dA dt, that we do not know, okay, is equal to the rate in, goodness gracious, which is 6 pounds per minute, minus the rate out, which is A over t, A of t per 100 pounds per minute. So there's the rate at which it's leaving, okay? The rate that's in the tank. So if you wanted to rewrite that, you have dA dt plus 100, A over 100, or 100A, is equal to 6. There's your differential equation. I know it. Don't worry, you don't have to do these, but you see they can all be set up, and it gives you a differential equation. Anytime you have a rate, that's a derivative. It may be something you know, like 6, maybe something you don't know, or it may be a combination of something you don't know with something you know. So, but that's sort of a classic problem like that. Okay? There is another type thing dealing with tanks, and this is draining rate, you might call. So these are just examples of different differential equations you could have. What if you have a tank, but this time the tank only has a flow rate at the bottom, okay? You're losing water in the tank. Now, by Torricelli's law, Torricelli could be a paper topic if you wanted to, or Torricelli's law could be, or any of these things, Newton's law of heating, cooling, any of these things could be used if you haven't chosen a paper top yet, states that the speed v of the efflux, the exiting water through a sharp-edged hole at the bottom of a tank, is when it's filled to a depth of h. So the depth here is h, okay, is the same as the speed that a body, in this case a drop of water, will require freely falling in gravity. In other words, the v, the velocity coming out the bottom here, is equal to, if you remember your physics, the square root of 2gh, okay, where h is how high that water fell from. But as the water goes down, the level goes down, so your h is decreasing, okay? So if it's a right circular tank, then g, of course, is acceleration due to gravity. The last expression comes from equating the kinetic energy, 1/2 mv squared, with the potential energy, mgh, solving for v, so that's where we got that one. So suppose the tank filled with water is allowed to drain through a hole under the influence of gravity. We'd like to find the depth h, so we want to know the variable h as a function of the time t remaining in the tank at t. That's what we're looking for, okay? Now, if the velocity of water out of the tank is this, okay, that is feet per second, say, or something like that, meters per second, something like that, centimeters per second, whatever units you're using. Well, then the area here, that area times that number of feet per second, that would give you the volume per second, okay, that is going to be exiting, okay, because area times height would be volume. So dV dt is equal to, now this is capital V, this is little v, okay, velocity. Don't get those confused. It's going to be equal to, we're going to assume a right circular tank. Oh, we're not going to worry with the dimensions of it. Okay, thank you very much. We're just going to call it A sub h. So this will be A sub h. Whatever the dimensions of the tank, that's the area. And that would be minus A sub h when it's at height h times the velocity, which is rho 2gh. Okay, so here we have a differential equation, but the volume of this would be h times a of h. Okay, so h is changing, the a of h is not changing, so they have two a's here, the volume of water and the volume of the tank. Okay, that's a problem here. But anyway, it comes up being a ratio of that. dH dt actually then is minus A sub h over A sub w, okay, times the square root 2gh. The point being that, I'm sorry, this is dH dt, because, like I said, the volume here is h times A sub h, and that's the area of the tank. So this is the area of the water remaining. So that's where that comes from. As h gets smaller, then, I'm sorry, this is the volume of the water remaining. What do they have? What do they call it? Rather strange the way they've worded this, but then you divide by, since this v times h is that, then v dh dt, you divide by, I'm sorry, they call the area A sub w. That's why you divide by that, and when you divide it by that, you get this. So dH dt is that. Weird looking. The point bit is that the rate at which the height is decreasing depends on the square root of the height, not that. So that wouldn't be a linear differential equation. That would be a non-linear, whereas most of the rest of these would be linear. But this is, see, you can separate this out. Square root of 2g, that's just a constant times the square root, or h to the 1/2. That then gives you a non-linear differential equation that you have to solve. Okay, that was the whole point of that. Same thing can be done with your circuits. I'm going over these really quickly because I'm not going to test you over these. I just want to give a flavor for what they're like. Here you have a voltage source, E of t. Okay, this is assuming here it's AC, because if it was a battery, there wouldn't be any change. This would be a voltage as a function of time. In other words, alternating current, alternating voltage. And it goes first through an inductor, L, then through a resistor, R, and finally through a capacitor, Okay? It's called a CLR circuit, you know, or LHR. I can't remember which title LRC circuit, series circuit. Okay? Now, what we know is that your inductor, the voltage drop across the inductor is that L times di dt. This is the voltage drop. Okay? Across the resistor is Ri. Voltage drop across the resistor is Ri. Now, the voltage drop across the capacitor, okay, is 1 over C times Q, which is rather bizarre, but the trouble is Q is I is equal to dQ dt. So basically what you have here is that Q is equal to the integral of I dt, okay, which is the integral of that. Now, that makes for sort of a different. So what you have to do is get away from current and get to charge. So this will be R times dQ dt. So don't go this route. And this will be L times d2q dt squared. Well, and then you've got that L times d2q dt squared plus R dq dt plus 1 over CQ is equal to E of t. And that could be a sine function or something like that. Alternating circuit typically would be. So now you have a second order differential equation, linear, okay, but still a second order differential equation. So L d2q dt squared plus R dq dt. Now, if you think, going back to physics 1, following bodies, Newton's first law of motion, and others too, it moves at a constant velocity. Okay, they're not. I thought they were going to introduce terminal velocity here, air resistance. They're not. Just keeping it fairly simple. You've seen those before. They're pretty simple. Let me, without going into gory detail about it, that mass times acceleration is equal to minus mg. Okay, that is the acceleration due to gravity. So get rid of the masses; they're not important. This is d2s dt squared is equal to minus g. Okay, it's a simple second order differential equation where that's just a constant. Okay, now if you had a initial value problem where s of 0 is equal to, guess what, s0, and s prime of 0 would be v0, your initial speed, then your solution to this would be s of t would equal minus 1/2 gt squared plus v0 t plus s0. Okay, and there's your typical one that we use in physics all the time. All right, well, what if rather than acting only under the force due to gravity, you also have air resistance that is what we call viscous damping? Then we have this. Let me see if I can still get this all in here. M dv dt, that is the change of velocity per change of time because of well, that's just change of momentum, okay? That's all that is equal to mg, that's your original, okay, minus kv, that is your viscous damping. In other words, your velocity, the force of which air resistance is some constant times your velocity, and that constant depends on your viscosity of the liquid, okay? So if you wanted to put that all together, where this is remembering that this is the same as m times d2s dt squared, because velocity is ds dt, so that would be this. And this would be mg minus k times ds dt. And then if you combine all these things together, you get m d2s dt squared, bringing this to the left-hand side, plus k ds dt is equal to minus mg. Okay, and that's, oh no, it's equal to mg. Oh yeah, because that was already on the right-hand side, so you don't have to move it. So there's your differential equation when you include the damping effect of air resistance. That would be this thing. K typically is pretty small for air, and at small velocities it's really small, so that's why we typically can use that first equation pretty easily. Okay, but as as the speed gets quite a bit larger, then no matter what your K is, that gets significant, so you have to include this. Now, if you were dropping into oil, the viscosity of oil is much greater, so then this would be a much bigger factor there, and you would actually reach a terminal velocity pretty quickly. Okay. Boy. The suspended cables, what you have there are trig functions. They basically, another way you can do this is talk about, I can't think of what the name of those are, brachoids or something like that, but you can break this down in a variety of ways. Basically, your differential equations there, when you have hanging wires, say power lines, this can either be suspension bridges, okay, or it can be power lines, okay, and they drop from one pole to another, okay. The same principle applies. You have a vertical force and a horizontal force, things are keeping you up. Your differential equation for both of these is dy dt is equal to w over t L, I think that is, where TL is your tension and W, I'm pretty sure, is the weight. I'm trying to find it where they define it here. I do not see it. Portion to vertical load, which is the weight. Okay, and that's what you get there. You have a different kind of equation. It looks rather simple, except it can get the weight's not going to change with temperature, but the tension is definitely going to change with temperature, as is the Y there, because of the cooling, the contraction of cooling, expansion of heating. This may sound a little bizarre. The big, strong power poles there, if the guys are running that cable and trying to save on cable and tighten those things up and running those lines in the summertime and tighten them up as tight as they can, and then in the winter when the contraction occurs, even though it's pretty small, but it's a long length of cable, that is going to contract, you're going to pop power poles. Believe me, that's strong enough to break a power pole. So you have to leave that. It's usually called the catenary in there. If you're running in the summer, you leave more. And running in the winter, near the coldest time of year, you can get it almost as tight as you want to get it, okay? But in the summertime, you have to leave that catenary because you know you're going to have that. So all that is involved in this. So this tension is not a constant, it's a variable, and that will change the Y, so you can have all sorts of problems with that. Okay. Now they have a little blurb here showing an Einstein-type character there. You can either, it says different approaches to the study of differential equations. We can do it analytically, which is working out the equation, working out possible solutions, saying these are the solutions, okay? You can do it qualitatively by just saying this is a function of all these things and it's equal to 0, or something like that. That leaves a bit to be desired. But in reality, a lot of these equations can't be solved analytically. Even though you can write them qualitatively any way you want to, you're going to wind up having to solve them numerically. And that's for another chapter. So that finishes 1.3. You really don't have to do much with this, except read through these and think through how you would set up the equations. 1 or 3, 5, 7, 9 or 11, 13, 15, 17, 19, 21, 23, and then you can do some of those others if you're interested. Additional math problem models, 25 or 27, and then there's some discussion. I'll let you take a look at that if you're interested. Another good thing to look at would be the Chapter 1 in review. Again, the odd number exercises have answers in the back, so any of those odds you could do 1, 3, 5, any of the odds 7 through 11, 13, 15, 17 through 21, 23 or 25, 27 or 29, 31 or 33, 35 or 37, and 39. All right. So that's Chapter 1. And let me see, I'm pretty sure I've got it here. I thought I had to run this off, but I must have forgotten to do that. Yeah. Okay. I have 3 of you. Yeah, I only got 3 in the class. I'll run these off at the end of class and give them to you.
What is that?
Huh?
What is that?
First test, Chapter 1 test.
First test?
Huh?
So it's like, hold on, I'm a little lost.
Okay. You have 5 minutes to complete. No, it's a take-home test.
Okay.
Okay.
Oh, okay.
Okay. I thought I explained that early in the term. Yeah, I didn't want to take up whole class time doing it. You can do it in 5. You got 15 minutes before the next class comes in. I'll give you 15 minutes. No, it's take home. Try to get it done within a week. If you can't, I'm pretty flexible and easy. But just get it done before I give out the next test. Okay. For your benefit, for everybody's benefit, because then if you make a mistake here, you may make the same mistake on the next test. If you wait till I'm giving out the next test, you don't get any feedback from this one. So get it back to me as soon as you can. It's not that big of a test. I will tell you this ahead of time. As you notice in most of those things we did, it's verifying this is a solution. So basically, even though I don't give you a lot of room here, once I run it off, you'll have the back side of the page. I'm not going to run off that. You have the back side, or you can include other pages. You have to show me how you verified this. The first one's just fill in the blank. You're taking a derivative. That's all you're doing. The second one is verifying that that can be written like it is. You're probably going to need a little bit of note. You might need a little bit of extra stuff to do the third part of that. Actually, top three, there's not a lot of actually. Number 4 is where it begins. Verify a one parameter family is an implicit solution of this. What you have to do is take a derivative and plug in and stuff like this. So you have to show me that. If you could do it all there or on the back, that's fine. If you want to include other pages. The rest of them, I think, pretty much, maybe the third part of number 2, you might have to do some extra. But then number 6 and 7, verify. So you're going to have more room than is given here, because that says a first and second derivative you have to take. So it's quite a bit. Some of it is, I admit, these questions came from the text, or from the same author of the text, and some of them just really, but they're all doable. Just take your time and do them. You won't be able to fit it in there. So either the back of the page or additional paper. With 6 and 7, it's going to require some other thing written in. Number 8 is verify. Okay? And number 9, you can pretty much just fill it in there. So any of those that say verify, you're going to take some extra room. So don't just fill in an answer, but don't show me how you got there. Yeah, we verified this is equal to that. Say, oh, this is equal to that. I gave you that in the problem, but you have to show that it is. So I'll run those off at the end of class. All right. How much time do we have before the end of class? About 15 minutes. So let's move on to 2.1. Finally, we're going to start actually solving some differential equations. Pretty much analytically, okay? But we're not there yet because they start this with what they call direction fields, okay? If this were calculus 1 and I said dy dx, what should you think? That's the derivative of the function y with respect to the independent variable x. What does that tell you? Slope of what? What line? Okay. Okay, that's the curve. That's the slope of the tangent line to that curve at any given point, right? It is the slope there. Slope of the tangent line at any point. Okay? Right, that's what first derivative tells you. All right, so what if we have some differential equation that's y is dy dx is equal to some f of xy? That's how differential equations look. First order may or may not be linear. It doesn't matter. That's a first order differential equation. But guess what? You can pick any. Okay. Have you a Cartesian coordinate, or a piece of graph paper there? Okay. Pick any ordered pair xy. You've got that function. Plug in there, and at that point, xy, give me a point xy. Give me an x, give me a y.
3, 4.
3, 4. Okay, at this point here, we go right 3 and up 4. At that point there, plug it in, and what if that's, say, plus 1? Then you know the slope of the tangent line right there is that. If it's 1/2, it's that. If it's 1/3, it's that. Okay, if it's 5, it's that. If it's -3, it's there. There's the slope of the tangent line. So what you can do is go around this board. There's a lot of points on the board. You can figure out the slope of every one and draw those little arrows there showing where that would be going. Okay? What this is called is developing a direction field. Okay? Now, if you know the value at any one of those points, then not only do you have the slope, you actually have y is, exactly what it is. Okay? And then you can follow approximately the curve and get the streamline or the curve that defines pretty much that function, if you know at least one point on that curve. Okay? So we call that the slope function or the rate function for that. The line segment that you would draw in there is called the lineal element. It doesn't have to follow that, but it goes pretty close to it. Now the direction field would be a whole series of those, filling out as many of those as you can. Okay? And sometimes some of them are pretty easy, and you just go for it. So let's do here the direction field for the differential equation. Here's the differential equation we're going to be dealing with. dy dx is equal to 0.2 xy. Okay? There is a differential equation. There's a Cartesian coordinate system. Okay? Not have too many, but more than we go on to fill in. Give me an xy ordered pair. Second? 0, 0. What's the slope there? 0. I kind of like that one. There's a tangent line there. Give me another point. 1, 1. What's the slope? 0.2, which is a pretty shallow slope there, about 1/5, right? Up 1 for every 5 over. So I don't know if I got it right, but generally. I want some easier ones. Like everywhere on the horizontal axis, y is 0, so all of these are 0. Aren't they? That's my kind of filling in the thing. And back here, they're all 0. Can you give me a few more? The vertical, they're all 0. You're absolutely right, because x is 0 on this, so they're all 0 here too. Okay? I like those. I can do those pretty quickly. Okay? But some of the others are going to take more effort. Okay? And you did 1, 1. 1, 2 would be 0.4, a little steeper. 1, 3 would be 0.6, a little bit steeper. A little bit, oops, too much. Let's say at 5, 1, 5. That would be 1. That would be a slope of 1. So this one got a little carried away. Okay? And going down here, at the negatives, you would again be, whoops. Now it would start going negative. I want to get that right. Whoa, didn't erase. No, it still didn't erase. There we go. All right. So you sort of get a general idea. 0.2, negative 0.2, negative 0.4, negative 0.6, negative 0.8, negative 1. Whoops. And negative 1.1. Okay, you could do one a little bit beyond that. Okay? And then at 0.2, at 2, 1, that would be 0.4, 0.6, 0.8, 1, 1.2. Okay? This would be 0.4. No, it won't. At 2, 2, that would be 0.8. Okay? A little bit steeper. So you can start filling all those in. Okay? Now this just shows the if you kept doing this, and we've already got a pretty good start on it, all that Victor has a book, so let me just show it here. Here is the direction field. These are going up like this. These are going down like this. Because this is going to have positive slopes here, negative slopes here, so down and up, and that's your zero. And sure enough, that's what your field looks like. So if you knew you were at some given point, you can almost back up and guess the curve that got you. Okay? So that's how we use direction field, just to give us ideas. Okay? Now, let's clear all the ink on this slide. And let's do example 2. Use a direction field to sketch an approximate solution curve for the initial value problem dy dx is equal to sine y. Okay? And we have an initial value y of 0 is equal to negative 3/2. Okay. Now, dy dx is equal to sine y. Now, I'm going to pick out some values here. They don't show their scale at all, which is really, oh, I'm sorry, they don't show this function at all either. What a pain in the neck. Oh, okay, they do show it there. All right. They're letting x range from 0 to about 5. Let's just do this. So this is 1, 2, 3, 4, 5. This is minus 1, minus 2, minus 3, minus 4, minus 5. Yeah, they're doing about the same here. 1, 2, 3, 4, 5, and minus 1, minus 2, minus 3, minus 4, minus 5. Okay, not quite the same as you got in the book. Okay? Now, dy dx is equal to, okay, y of 0 is equal to negative 3/2. So here is where you're starting right there. You're at this point right here. Now, okay, they draw a bunch of curves in here. Let's just start with that. What is the slope at 0, negative 3/2? Okay? dy dx is equal to sine y. So, negative 3/2. All right. Let's just pause a minute here. When y is equal to 0, right? Where is that? The x-axis, right? Y is equal to 0 is the x-axis. What sign of y? Everywhere that y is 0. Yeah, sign of 0 is 0. So let's just do like we did last time. These are all going to be 0 slopes here. Now we don't need that, okay? But we need it sort of as a reference, okay? Now where else is sine of, what else is equal to 0? The next 0 you hit for sine. Pi, right? Yeah. Someone say pi? Yeah. Sine of pi is 0, right? Well, what is pi? 3.14, right? So just beyond 3. So here you have a bunch of zeros again. I'm not sure is it 3.14, but you get the idea. Okay, so those are easy to put in. Right? All right. Now, the sine of minus pi halves. That's about 3.5, isn't it? Did I put that in the right place? Yeah, minus 3/2, okay. Y of 0, so when x is 0, y is minus 3/2. That's really close to minus pi halves, right? Pi halves is 3.14 over 2. This is 3 over 2. So it's minus, and what is sine there? Minus pi halves. Oh wait, I'm sorry. Yeah, minus pi halves. Sine is 0 here and here. Sine curve goes like this and like this. So what's sine down here?
Oh.
Minus 1. Okay, so down here, all these slopes are about minus 1. And I really don't care about those over there. That's the only one I really care about. But all these are about minus 1. Okay? Now, as you're going down there, here at 0, it goes slightly more negative, and then at that point, it goes slightly less negative. So basically, your curve here is something like this. It has to be. Where that's the slope of minus 1 there, it's 0 here, and it's slightly more negative as you go, and slightly less negative in inflections out here. So that is pretty much, given that, that's going to be a really good guess of what that is. It can't ever go past 0 there, you know, when it gets on out there, and up here, it never gets anything other than 0. But there, the slope is negative 1, and it's less than that before that, greater than that. That's it. That is pretty close to being what you've got here. And that's just what they showed here. Or pretty close to it anyway. Right? See how you do these? It's sort of, it just gives you a general idea, it doesn't give you exact. Okay? That was example 2. All right? By the way, there's a name for this, and this is called the method of isoclines. Isoclines, iso means same, cline basically means elevations or slopes. So that's what we're doing, isoclines. We'll start next time by autonomous first-order differential equations on page 2.1. Let's see. Homework exercises in this set would be 1, 3. The next one says a computer software coming up with direction field. Try to do these without computer software. Any of the odds 5 through 11. Okay? And stop there. We'll pick up the rest of those next time. Okay. Do y'all have a moment?